killing the cat becomes a superhero. And then all the enemies you fight are the other particles which you haven't learned yet, but you will in the future. Like the different types of particles, leptons, quarks, bosons, hadrons, and things like that. So I almost forgotten about this game until like suddenly I remember it for some reason earlier this week. But in any case, so at least we have one person gonna present today, Jia Cheng, and maybe someone else. So we will do that in the second hour. But for now, let us continue talking about our postulates of quantum mechanics. We only discussed 2 until now, right? Because we are still slowly learning and getting used to Hilbert space. So let us continue for the next postulate. It is about what happens when an observation is made. Okay, so we know that it affects the superposition. Because on last Monday's lecture, I have shown you that the Feynman experiment, right, or the Feynman's description of the experiment, if you do not observe if you don't observe what happens to the electron before arriving the screen, you will get the interference pattern. But if you actually follow the path of the electron, if you know the electron goes through slit 1 or slit 2, actually don't even have to follow all the way, like one of you asked last time. You just need to know whether it's going through slit 1 or slit 2. Even that information alone destroys the interference. So in summary, if you don't look at it, you get the interference pattern. But if you look at the experiment, you get this, the interference is destroyed. So how do we formulate this in terms of our equation, right? So this is why we are using Hilbert space, which is a very weird vector space with complex numbers. It is so that the results and the outcomes of what happens in the experiment can be represented in an equation. And once you have something in an equation, you can write down the laws of quantum mechanics. So this is the statement of postulate 3. So what happens when an observation is made? So this is one of the third postulates. So postulate 3. Okay. So postulate 3 says that, well, we have, remember what I said last time. A state is a vector in Hilbert space, the ket, right? So I have a ket, and then the measurement is represented by some operator. So let's consider a system. Okay, so sometimes we call it a system, but usually the system is just one particle, like the electron, right? So the system or the particle is in the state psi, okay, and then an observable Q is measured. Okay, so remember what we say in postulate 2, observable is a Hermitian operator. Okay, and then what happens when we measure a state? So there are 2 possibilities. When the state happens to be an eigenstate of Q, right? So if this happens to be a eigenstate, I also talked about eigenstate last time, I hope you remember, right? An eigenstate. So therefore, if I have a Q operating on this state, I just get the eigenvalue coming out and back to the same state again. So the measurement will definitely yield the eigenvalue Q. So the corresponding eigenvalue Q. So this is a definite outcome. So this is almost like Newtonian mechanics, because you know, even before observing, you know what you're going to get, right? But this is only when the particle is in the eigenstate, right? So in quantum mechanics, the strange thing happens when the particle is not in an eigenstate. If it's not in an eigenstate, that means it is some superposition of other states, right? Because another thing we discussed on postulate 2 is, once you got the operator, you can find the eigenstates, and we can use the eigenstate as a basis, and every other state can be created as a some linear combination of this basis. But in general, if it's not an eigenstate, then no longer Q acting on it gives the eigenvalue. So if psi is not an eigenstate, the outcome is not definite. Okay, of course we shouldn't give up here. Even if it's not definite, we can still kind of understand what is going on by getting the probability distribution. Okay, so we don't know where, but it's not totally random. We can calculate the probability distribution. So that is what we want to do for the most of quantum mechanics, our entire course. We want to calculate the psi. Once you get the psi, we can get the probability distribution. So the outcome is not definite, but we'll follow a probability distribution. Okay, and then if it's a probability distribution, then what will be the average value of your measurement outcome? Right? When it comes to probability, what do you calculate? The mean, the average, or in statistics they call it the expected value, right? So with expectation value, I use this symbol, right? I think you guys are taking probability and statistics now, right? With Dr. Chin. Is it Dr. Chin? Yeah, right? So expectation value. So you'll probably be dealing with this also. And actually from quantum mechanics, we calculate this by the bra-ket. So it's, if the state is psi, you sandwich them between a bra and a ket. That will give you the expectation value. So remember, a bra, this one act on it becomes a new ket, and then you put a bra there, it becomes a number. So our expectation value should be a number, right? So that is how we calculate the expectation value. Okay, clear so far? Yeah, you're taking that course, huh? The game is on Steam. Okay, I think wait for sale. Then you can. It's a 2014 game, so I expect if it comes on sale, it's gonna be super cheap, right? Like $5 or something. But yeah, so so it is a good thing that you guys are learning prop and stats with Dr. Chin and doing this at the same time, because we're kind of like the same thing, right? So you don't have to multitask. Although the notation will be a little bit different, but it's still, at the end of the day, it's a probability and statistics. So let's take an example. Hang on. I heard something. Is it me or you? Okay, I'm recording, right? Double check. Yes. Yes. So let's take an example. I always go to the 2-dimension for the simple example. Consider a 2-dimensional Hilbert space. Right? And then let's say the eigenstates of Q as the basis. Right? So eigenstate is E1 and E2, and I will use that as a basis. So recall what I said last time. Once I got a basis of a vector space, it's like the generalization of IJK last time. Once I got a basis, I can use this to build any other vector. So an arbitrary vector can be written as some number E1 times another number E2. And in fact, I remind you how to calculate this number. I take E1 close with the state, and this can be calculated by E2 close with the state. Okay, and this, we are using the eigenstates of Q as the basis. So that means if I Q operate on E1, I get a eigenvalue back to E1, and then if I Q operate on E2, I get its E2 eigenvalue on E2. Okay, so this is the situation that we have right now. So if my particle is in this state, it could be any number, right? I can calculate the expected value of Q. So if I measure Q, some observable, maybe energy or the spin, whether it's up or down or things like that, right? So the expectation value of Q is what? Well, according to postulate 2, we do this. So what you do is you take the psi and then you sandwich this and then this. But what was psi? By psi was this thing over here. So it is the dagger of this. So psi 1 bar E1 and then psi 2 bar E2, right? And then I sandwich this with psi 1 E1 and then psi 2 E2, okay? And let's see what we get if I, well, just multiply this inside. So this one is still the same at the moment. Okay, can you see? Right? But I do this first. So the Q goes into here. This is a number. The Q is an operator. So the number, I can push it aside because the Q operates on the vector ket. And once I operate on it, it becomes psi 1. The Q operate on it, it turns into a lambda 1, right? So yeah, let's put the lambda 1 on the left. It doesn't matter, it's a number, right? And then this is psi 2. The Q operates on E2, becomes a lambda 2, okay? Now I expand this bracket, but remember the states are also normal. So E1 close with E1 becomes 1, E1, E2 is 0, right? So E2 by itself is also 1. So that means only E1 times E1 is non-zero. So E1 times E1 becomes what? Becomes lambda 1 psi 1 bar psi 1. And then this one, oh, E2 multiply becomes 0, gone. E2 times this also gone. E2 times this E2. So it becomes a lambda 2 psi 2 psi 2, right? So what is lambda psi bar times psi? The complex conjugate number times itself is just the absolute value, and same thing here, the absolute value, okay? So this is the expectation value. But then this is where we make a realization. When you learn probability and statistics, right, what does it so let me write it here. In probability and statistics, stats, right, the expectation value of Q, right, which is the symbol, I write this here, is the value that I want to calculate times the probability of this happening, and then the value that I am calculating for case 2 times the probability of this happening. So if I compare these two equations, right, we conclude that the psi 1 is the probability that the particle is in state E1, right? And similarly, psi 2 is the probability in state E2, okay? So the psi 1 coefficient, the complex conjugate, is actually telling you the probability. Well, the absolute value will be the probability. The psi 1 by itself not yet, it's not yet the probability, right? So it's the square root of probability with complex numbers, okay? So let me generalize this to an n-dimensional Hilbert space. Okay, so this is how we, from the wave function, we can calculate the probability distribution now. So now we have almost a lot of the important things, how to get expectation value, how to get the probability, right? So generally in any dimension, right, could be 1-2 dimensional Hilbert space, or it could be infinite dimensional. Chapter 3 will deal with infinite dimensional Hilbert space, but actually a lot of the concepts are the same, right? So let's take the eigenstates of Q as the basis. So I'm just basically repeating what I did just now, but for n dimensions. Eigenstate of Q as basis. So we want to measure Q. So let's take E1, E2, dot dot dot, En, right? So all these are eigensets of Q. So that means Q operate on any Ej. I will get the eigenvalue and then back to Ej again. Okay, so this is the situation that we have. Then a state psi, any state, an arbitrary state psi, I can write this in this basis. In this basis as psi 1 is equals to, well, the coefficient 1 times E1, coefficient 2 times E2, coefficient 3, dot dot dot, until the last one, En. So to make it short, I write the summation from j from 1 to n psi j, and then this is any j. Okay, so this is a summation from 1 to n, and of course again the psi j itself. How do we calculate the psi j? I take the j and dot with the inner product with the main state, and this will isolate the specific coefficient for the jth component. Okay, so why am I repeating this? Because it is good to practice notation, because we will be using the Kronecker delta now. Okay, so let us calculate the bra. So let's take the dagger to calculate the bra. So I take the bra is basically just dagger everybody, right? So dagger everybody. So the sum is from let's write the index from k to 1 to n. Right, it doesn't matter what letter I use, but let's take k. So dagger, right? So dagger, the complex number becomes conjugate, and then the ket becomes bra. Okay, so it becomes this thing now. And so how do we, so this is a state. So remember when we say that state must be normalized, right? So let's see what happens if I take the inner product by itself. So psi bra-ket psi. So that means I take this multiply by this. So what I have here is the summation from k from 1 to n, psi k bar e k, k, right? And then on this one is j from 1 to n, psi j, e j. Okay, so how do you multiply these two? Well, this is a double summation, but it's basically just expanding the bracket. So it's not that difficult, right? It's just summation from k from 1 to n, summation j from 1 to n. The numbers come together, and then this thing multiply together. And this is where Kronecker delta will make our life so much easier, and to me so fun to use, because what is ek times ej, right? It is only equals to 1 when these two are the same. The minute they are not the same, it becomes 0. So this is the Kronecker delta ekj, right? So let me remind you what is Kronecker delta. Is 1 if k equals to j, 0 otherwise when they are not the same. Okay, so even though I have summing j and summing k, but this is only relevant when k is equals to j. Okay, so let's say I sum over j, right? So if I sum over j, everybody is 0 except the one that happens to be the same as k. So that means I end up with k from 1 to n. Only when j is equals to k, then this term is equals to 1, and everybody else becomes 0. So this is actually the summation of k from 1 to n see, the same number complex conjugate. So this is the absolute value square. Okay, and these are the probabilities, right? So just now we say that the psi k are the probabilities, of getting the ek. So we call this ek, right? So this is the reason why we want the state to be normalized, because I want this sum to be 1, and the reason is because in probability and statistics you learn that the sum of probabilities must be equals to 1. Okay, So we are using some fancy notation here, but at the end, yes, we are back to probability. The sum must be 1 because it's talking about percentages, right? So what is the chance of getting this? What is the chance of getting this? And stuff like that. Any questions so far? Okay. So this is only the normalization, right? We were supposed to be talking about the expectation value. So let's calculate the expectation value. Of Q, right? So as I said, the interpretation here is that if I have a state of this, then this is the probability of getting the state K. But what is the expectation value? So I want to calculate this thing. So that means I need to do, well, I sandwich Q with the bra-ket, right? And on the left side, we got sum over K from 1 to n, psi K bar, and then EK. And then I sandwich the Q, and then I sum over J from 1 to n, psi J, EJ. We do the same thing as before. We keep this aside first, so K from 1 to n, psi K, EK. And then the Q I operate here, right? So Q I operate here, this becomes sum over J, psi J, and then I Q operate, this becomes lambda J back to EJ, right? And then I multiply these two together. So this becomes a sum over K and then a sum over J, and then psi K bar psi J, lambda J, and then EK, EJ. So same story as before. This is the Kronecker delta. So the Kronecker delta says that the sum of J, most of them will be 0 except the ones that are equal to K. So when they're equal to K, I got psi K bar psi K, and then only when this equal to K, then I get non-zero. So this is equals to the sum over K, from 1 to n, I was lazy to write, and then psi K, this is the probability times the value. So this is the same formula for expected value that you will use in probability and statistics. Okay, very easy, right? Maybe like for the first time you're not very used to doing this, but so this is the method, right? So I'm showing you the method, then from after this you know this is the method, then you just make use of this to solve your question. So hopefully after this, after I show you, after a few practice, it will become easier. Okay, what time are we now? 9:25. Any question? Bra-ket is inner product. Yes, exactly. Wait, what was this? Yeah, lambda K is the eigenvalue. Yeah, so the eigenvalue of Q, yes. So I kind of breezed past this a bit too quickly, right? So just now I have an operator Q, right? And then I have the eigenstates. Eigenstates E1, E2, and so on, right? So this means Q times, okay, let's Q times E1 is the first eigenvalue and E1. So the lambda here is the eigenvalue, right? Corresponding to E1. Okay, so then yeah, then why does the delta, someone asked about the delta, right? What does it mean in physics? Because there's two summations, okay? There's two summation here. So when I sum over K and sum over J, right? And if I sum over J first, I sum over J, right? The K is still, K is a long list from 1 to n. J is also from 1 to n, right? and then canonical delta. So actually, let's do an explicit example. I think it will be clear. So let's take a two-state. Let's go back to two states, E1 and then E2, right? So this is a two-dimensional Hilbert space. Okay, so what we are doing here is we are doing a summation from, I want to find the expectation value of Q, so I sum K from 1 to 2, J from 1 to 2, right? And then psi K, psi J, lambda J, and then this is inner product EK, EJ, okay? So let's write everything out. Let's write everything out explicitly. That is going to be tedious, but I think if you're not used to it, then it's worth to do it, okay? So I keep the summation of K outside. Let's sum over J. Let's write J out everything. So sum J from 1 to 2. So that means I psi K, psi 1, lambda 1, EK, E1. And then the second term is psi K, lambda 2, lambda 2, EK, E2. Okay? So this is summation over J, and then this, look at this term over here. This is EK times E1. So EK times E1, so it's only non-zero if K equals to 1, right? But this is non-zero if K is equals to 2. So what you have here is this becomes, it comes back to, or should I just write everything out more explicitly? So let's, should I? It's gonna double the notation, but let's do everything. Right, so psi 1, lambda 1, this is E1, E1, and then so this K equals to 1. K equals to 1, and then I do plus K equals to 2, K equals to 2, right? So this term is 0, this becomes 1, so I come back to psi 1 absolute square, and then psi 2 absolute square lambda 2. So this is the same as summing either J or K. Let's say this is K from 1 to 2, psi K square lambda K. Am I right? So the summation should still remain. Operator is determined by state or state determined by operator. Both. Okay, both. Because remember, yeah, so that so in that sense, previous lecture was important. An operator, right? Q, Hermitian. Okay, so we have shown that this one has eigenstates. So I got E1, E2, En. So in that sense, given the operator, you can determine its eigenstate. So the operator determine what are the possible eigenstates, which states, but it doesn't determine the system, right? It just tells you what are the eigenvectors. Okay, so we are just talking about vector. Like for example, in R3, IJK are vectors, but we haven't even starting to discuss the position of a particle yet. We're just talking about the IJK by itself. So it has an eigenstates, and then we use as a basis. So operator determine what are the eigenstates, and then the eigenvalues are like this, and so on and so forth, right? So this is just an operator. It represents a physical measurement, which we haven't done yet, right? So it's just to say that we want to measure something about the system. This will be the outcome for example, the electron interference, right? Let's say if electron or the cat is dead or the cat is alive. So there are two possible states, two possible outcomes, whether it's dead or alive, right? Whether it's dead or alive. But the system itself, the physical system, is some vector in Hilbert space. But if this is a basis, then I can write this as a linear combination of the basis. Okay, so that we haven't talked about physical system yet. So remember, we are still in chapter 1. We are just establishing the rules of the game, like you said last time. In chapter 2, so wait until chapter 2. We will actually do and discuss an experiment, and we see how operator, what does the operator mean in an experiment, what does the state mean in an experiment, and so on and so forth. Correct. Yes, operator represent all the state of the system. Yeah, exactly. So lambda determine the eigenstates. I guess this is related to what we discussed just now, right? And eigenstate has the corresponding eigenvalue. The lambda will be the measurement outcome. You can just imagine doing some experiment and then your apparatus will give out the reading, what number it is, then that should be the outcome. For example, the ground state of the hydrogen atom, the eigenvalue is 13.6 eV. So I guess let's so it's going to be a bit confusing. Let me just summarize of what we discussed so far, right? So of what we have so far. Okay, so just now I'm talking about an observable Q, right? This is a Hermitian operator, and postulate 2 says that it has a complete set of eigenstates. Okay, so complete is important because when it's complete, then we can use it to as a basis. If it's incomplete, that means it's not enough to make a full basis. Then I cannot write down some vectors. So I can use this. So these are the eigenstates. And I use this as a basis. And I also told you last time there are different bases for a Hilbert space, but we can use this as a basis. So then given the setting, right? So I know I want to measure Q. Then if I have a state, right? So I have a state psi that is the sum of some arbitrary linear combination, depends on what number this is. The probability, well, the psi itself is not the probability, but we call this the probability amplitude, corresponding to, let's say, some other number ei is the probability I, which is calculated by ei psi. Okay, so this is only the probability amplitude, and this is still a complex number. This is why we cannot say this is a probability yet, but the actual probability of observing ei is the modulus square. So I calculate ei psi modulus square. Okay, so I square this to get the probability. Okay, and then what else do we have? Postulate 3, right? The expectation value. Because if it's in some superposition, you see, right? If it's just, if the state is just, let's take for example just E1 by itself, it's just one term. If it's just one term, then the probability is 1 and all the other probability is 0. But if it's a sum of multiple terms, then I got many different probabilities that sum to 1. But in any case, the expectation value of Q is given by this, right? So we did this calculation just now, and it happens to be the same formula as your probability and statistics expectation value. Okay, let me write this thing down here. It will not be that important for now, but generally, if you don't understand this, ignore. But just since we are here, I want to be complete. The transition amplitude from state psi to phi is phi psi. Okay, so this is a generalization of equation. This is like given a state psi, what is the probability of getting the eigenstate? But given a state psi, what is the probability of getting another arbitrary state phi? So this is the equation 2. Okay, so this is what we call the transition amplitude. But this is not important, so never mind for now. But yeah, so this is the main points of what we have been discussing so far. What's the physical meaning of inner product? It's like a dot product lah. You know, just like in Newtonian mechanics, what is the physical meaning of the dot product? Is to get the length of the vector, right? So here you get the norm. So another answer to your question is, this is an inner product. This gives you the probability amplitude. Then if I square it, I get a probability. This is the inner product. But if I take if I sandwich the operator with the bra and ket, then the meaning is the expectation value. So it depends on which dot product are you talking about, which inner product are you talking about. Okay, is the eigenstate the same as eigenvector in this course? Yeah, we treat them as the same. It's the same actually, because postulate one says that remember postulate one states are vectors in Hilbert space, right? So all of them are vectors in Hilbert space. So that's why I say eigenvector is the same as eigenstate, because we are talking about the same thing. Okay. Maybe yeah, I think it will be clear if we do a concrete example. Okay. How did people invented this? Yeah, right. Schrodinger. Those people are Planck, Schrodinger, Heisenberg, all those people. They took quite a few decades to figure this out. Where are we now? Let's do 1.4. We are supposed to be at 1.4.4. Okay. Yeah, so I think it will make sense more if we see a concrete example. So we are measuring the spin of an atom, right? So at the moment, just imagine the atom to be rotating, because we haven't talked about the details of the spin yet, but just imagine them to be rotating about some axis. So is it clockwise or anti-clockwise? Then that is a very rough language, but just to avoid confusion, yeah, just imagine this: clockwise spinning or anti-clockwise. So let's say this is anti-clockwise if is +1, and we call this spin up, and -1 if it's spin down. Okay, so what we have here is we are measuring the spin. So I guess let me write down what happens here instead of just reading off the lecture notes, right? So we are measuring the spin. Of an atom, right? So the operator, because when we measure something, we need to have some operator. The operator is going to be sigma z, right? So let's treat this as a given formula for now. And then I have eigenstates, spin up, which is written in this form, and then eigenstate spin down, which is written in this form, right? So this state means my particle is rotating this way, my axis is here, and this state is rotating this way, so the axis is down. Okay, so I have two eigenstates, and then the eigenvalue, we can easily check the eigenvalue. We have done this on the previous class already, right? If I take this operator and multiply with this state, I'll just get a positive number, right? But if I try this multiply by this, I get this number. So the eigenvalue of the state is +1. The eigenvalue of this state is -1. Okay, so that's all it means over here. Okay, so we do a few cases for this example. This is page 4, this is page 4, this is page 5, right? So let's consider case 1. If atom is in state, the state of my atom is, let's say, this, okay? Then what is the probability of observing the atom? So I'm measuring the spin of the atom. So if I observe this atom in this state, do I see it doing this or do I see it doing this? What are the probabilities? So the probability of getting of seeing the atom doing this, right, is the probability is by the postulate. I told you that it is the amplitude is taking this on my state and then I square, but this is this specific state, so it's just up square, so it's just 1. Okay, so this transpose times this, you just get 1, right? And then the probability of getting down, so it's rotating the other way, is the probability down, so you do down psi, but psi is pointing up, so you're taking the inner product of two orthogonal vectors, you get 0. Okay, so the expectation value is sigma z is just well, psi sigma z psi, so you can compute this is just up sigma z up, so sigma z times this is +1 times up, so it's just 1. Okay, so on the other hand, if atom is in the state, so I'll give a different state now, right? This is what postulate 3 says. Postulate 3 says that if the object is in an eigenstate, right, it's just an eigenstate, exactly this eigenstate, then I will get 100% chance of what we expect, right? 100% chance, and then everything else is 0%. But if it is not an eigenstate, so this is definitely not an eigenstate of sigma, so what is the probability of getting up? So the probability of getting up here is, well, the amplitude is this, and how do we calculate this? So this is the absolute value square of, this is a 1 over square root number, so I move it to the front, and then I just need to inner product with this, right? So you see, this times this get 1, this times the other one will get 0, so it's just 1 over square root 2, 1 plus 0, but you whole thing square, so you get a half. Okay, then what is the probability of getting down? Then you calculate for the down. So same method here, but this time you close the inner product with the down. Right, so it is 1 over square root 2, but this times this gets 0, but this times the back gets 1, so this is 0 plus 1. But it's still half for this example, right? So it's a equal superposition, 50-50 chance of either getting up or getting down. So if the state, this is like the Schrodinger cat, you don't know whether it's dead or alive, it's a superposition. Okay, so before you observe it, you don't know what is it doing. Okay, but if you observe it, there is some chance to see it's spinning up, right? Or another chance to spin the other way. So that is the probability distribution, similar to the Schrodinger's cat experiment. Yeah. Yeah, this is kind of amazing, right? Because well, this is 100 years ago, I think. Yeah, so let me remind you one more time. I have a state and I have an eigenvalue. Right, so I have a state and I have an eigenvalue. Because this is my eigenstate, if I operate on this, the eigenvalue is plus 1. If I have the other state operate on this, the other eigenvalue is minus 1. Okay, so the eigenvalue is the outcome, right? Plus 1 means, oh, I know it's this way, clockwise. Minus 1 means anti-clockwise. Okay, so one more thing we still haven't done, expectation value. So let's expectation value. So what is the expectation value for this state? So I take the psi, and then sigma z, and then have the psi, right? So this part is 1 over root 2, up and down, and then I sandwich this with this thing, so I got 1 over root 2, up and down. Okay, so 1 over root 2, 1 over root 2 is just half together, right? And then the up is here, and then the sigma, I operate this. Now you see what happens. The eigenvalue is important, right? This eigenvalue is plus 1. This eigenvalue is minus 1. Okay, so now let's see what happens. This times this is 1. This times this is 0. This times this is 0. This times this is minus 1. So the expectation value is 0. Right? So of course it's 0 because I am equal superposition between plus 1 or minus 1. Right? There's a 50% chance I get plus 1, another 50% chance I get minus 1. So 50-50. So what is the average of plus 1 and minus 1? In the middle, 0. Okay, so in the middle between of plus 1 and minus 1. Make sense, right? So this is how you deal with expectation values. This was the, it can be different states. It can be different states. Okay, so we will learn how to do this technical stuff later. Okay, so we will learn how to do this later. Yeah, for now, let's treat this as a given formula. It's a given to you. So if it's the same number, then it could mean different states. Yeah. So by coincidence, two different states can have and the same eigenvalue, right? So A, right? So let's say I have two eigenstates, right? So A times beta is beta, right? So let's say A and alpha are different. Different state means alpha, beta. Different eigenstates means they are 0. Okay, but alpha may be equal to beta. I would say by coincidence, but there's a technical reason. It's not a random coincidence, but this is the topic of degeneracy. Degeneracy. Okay, so you may have encountered degenerate systems before, like the hydrogen atom, right? Hydrogen atom, only one state got the 13.6 electron volts, and then the first excited state is degenerate because you have a different spin, different states with the same value. Do you learn this, right? The L quantum number, the different L quantum number give the same N and that kind of thing. So that is where it could be the same. Okay. 953. Oh, so in other words, degeneracy was the question just now. Different eigenstate have the same eigenvalue, right? It's just a fancy word. Yeah. So don't need to confuse about degeneracy. It's just like exactly what you are wondering, right? Could there be, is there a chance that the two eigenvalue happen to be the same number? That's degeneracy already. Okay. So yeah, so we spend almost the whole time only talking about postulate 3. So let's at least try to start postulate 4. We are talking about compatible observables. And time evolution. So this will be discussing postulate 4 and 5. We haven't even mentioned Schrodinger equation yet, right? Which is the most important equation of this course. Okay. So what do we mean by compatible? Another fancy term you have already encountered. Anything that is incompatible will have the uncertainty principle, right? So let's say two observables. Why is it so dark? Two observables A and B are incompatible. So not compatible if there's an uncertainty principle between them. Right, for example, the uncertainty in the A measurement times uncertainty in the B measurement is greater than some number. Okay, so this is nothing fancy because you have also already learned this in modern physics. The standard example is position and momentum, right? So these are something you can observe. By postulate 3, there is going to be some operator which I will call X and some operator which I will call capital X, capital P. And then the measurement outcome is delta X, delta P. The uncertainty will be greater than h bar over 2. Right? So this is something that you learn from modern physics. So I'll just mention this briefly. This was like what you did last time. And now I'm just saying in the language of compatible observable, it just means that position and momentum are incompatible. Okay? So let me state postulate 4. Okay, and then we'll take a break, right? So there is always a set or some set of compatible observables actually this doesn't really say much. Because observable just depends on what we want to observe. The more important statement is they are compatible if they have a common set of eigenstates. Okay, so in other words, just now was in the case of incompatible. So if they are compatible, right, they have the same set of eigenstates. Okay, so let's say E1, En. Okay, previously we only focus on one operator, right? So one operator, I got the eigenstate, and then let's start with E1 now, then lambda 1 and then E1. And then if they are compatible, that means B also have the same it may not be the same number, but it's the same eigenstate, right? So this is the eigenvalue. This is the eigenvalue, right? But these two eigenvalues do not need to be the same, or may not. But postulate 4 says that E1 is the same for both. Right, so the main point is the states are eigenstates. So operator acts on it, you come back to operator, come back to the same ket with some coefficient. You act on this, you come back to the same ket again with some coefficient, which may or may not be the same. No, don't know, right? It depends on what problem you are solving. Okay. So yeah, does anyone have any question now? Physical meaning of what? You mean physical meaning of degeneracy? Well, physical meaning of degeneracy, it just means that, yeah, same energy, right? Like the hydrogen atom. The first excited state got different states with the same energy. So let's take a 10 minutes break. We come back at 10:59 and then we will hear some of your presentations. Okay, so let me stop the recording. About the postulates of quantum mechanics. Postulate, where were we? Postulate 4. Okay. So, yeah, so tutorial 1 is mostly about how you play with the bra-kets and that kind of thing. So a lot of it is still based on the linear algebra methods. And yeah, so what Hong Yu commented just now, is it the same as the physics? Is exactly the same. So because the physics student also taking the same linear algebra class on the previous semesters. So, and Hilbert space is a linear vector space, so everything is the same. So, but now we want to discuss about the compatible observables. Okay, so the idea is that we have things like uncertainty principle, and am I sharing screen? No, I'm not. Let me share. So we have things like uncertainty principles, and there are other pairs of observables that do not have uncertainty principles, so they are compatible. And the point that we want to make here is that when we have compatible observables, then they share the same eigenstates. Okay, so we got this, right? So now let me write this out one more time. Let us see what are the consequences of this having the same eigenstate. So let me write this statement one more time. If A and B are compatible, there's a common eigenstate. Right? So let's call this eigenstate E. So that means if I operate A, yeah, so remember I always do the operator acting on the flat side of any ket. and then I get the eigenvalue, and then back to E again. Okay, and then if I take the second operator, if they share the same eigenstate, they are compatible. Maybe I get a different eigenvalue, but I will call this equation 1, and I will call this equation 2, right? So now let's play around with this and see what we get. So let's, just for fun, let us operate B on this, both sides of this equation. So I'm going to apply the operation of B on equation 1. Let's see what we get. Right, so if B acts on 1, that means I say B times A acting on E, and then B times AE. But A is a number, so I can move the A aside. But operator, I cannot anyhow move. Operator must be important. B must be on the left. Because matrix multiplication may not be the same, right? So they may not be the same here. But A is a number, I can just anyhow push it aside. So I got B times this. Then B operate on E. So B operate on E, I got A times B times E. Right. So the conclusion that we find is that BAE is AB E. But important to remember, generally, BA may or may not equal AB. Okay, they may or may not equal, but I'm about to prove that they are equal. Okay, so then let's do the other case now. Let's look at equation 2. So this equation 2, for fun, let me operate A on this B. So I apply A on equation 2. Right, so I got AB times E, and then so the same story happens here, right? So A times B times E. I can, B is a the small b is a number, so I can push it aside. Then I got AE, but E is an eigenvector of A, therefore I got BA times E, right? So I conclude that A times B E is equals to, this is the number, so this is BA times E, right? So I got this equation 3, and then I got this equation 4. So I will prove that if they are compatible, if they share the same eigenstate, AB is equals to BA, right? So I will take equation 4 minus equation 3. So I take this equation minus this equation. So I got ABE minus BAE, right? And then this minus this. So BAE minus BAE, right? This is a number, so I can flip them anyhow. So these two are the same. So they cancel each other. But these two, well, AB minus BA, I can factorize out the B. This is true. Okay. So this should be eigenstate, so it's definitely not a zero vector, right? So we find that we conclude that if A and B, how did we start this calculation? We start this calculation by requiring they have the same eigenstate. So if A and B share the same eigenstate, then AB is equals to BA. Okay. So do you get what I'm trying to say here? If A and B share the same eigenstate, then AB equals to BA, right? So from here because whether the order of operations are the same, if you swap the order, this part is an important concept, so we're going to define the commutator. So I will define something called a commutator. Right, so commutator means I write this notation, A bracket, so this is AB, this means AB minus BA, right? So that means to say that if A and B commute, means A bracket B equals to 0, which means that AB minus BA, or in other words AB equals to BA. AB, right? So we have shown that by postulate 4, this happens if they share the same eigenstate, or if they are compatible. Okay, but generally, if let's say I have two other operators, so let's say P and Q are incompatible, then the commutator between P and Q are not zero. Okay, clear so far? What page is this? 5, 6, 7. Okay, so let me give you an example. So let's give you an example. Let's say I measuring spin along the x direction. So I will give you the formula first. How did we get this formula? We will explain in a later chapter, but let us start with this first. Okay, so if I want to measure a spin of an object, because previously, right, when we were talking about the spin of the particle, we were using the z-axis, but I want to calculate the x component now. So is it rotating this way or the other way? So this is my spin along the x direction, and then I also can measure a different direction, the y direction. So these are two observables, but they are not compatible. 0 minus I 0. Okay, so these are not incompatible observables, because let's calculate the commutator. Let's see what happens if I take sigma x times sigma y, right? So if I take sigma x and sigma y, is a 0 1 1 0, and then 0 minus I 0. So if I multiply these two matrix, I got I and then 0, right? And then 0 and minus I. Okay, so this is sigma x times sigma y. But remember, matrix multiplication, if I swap the order, there's a chance I get a different number. I will for here. Look at this, right? I 0 and then 0 1 1 0. So if I multiply this, right, what do I get? 0 minus I, and then 0 0 and then I. So these are not the same number. It's a difference by a minus sign. Okay, so we calculate the commutator between sigma x and sigma y, which means I want to calculate sigma x sigma y minus sigma y sigma x. So that means I take this minus this. So if I take this minus this minus this minus negative I just get 2i 0 0, and then this is minus 2i, right? So in other words, this is just 2i 1 0 0 minus 1. And actually, what is this? This is something familiar. This is actually sigma z. So the commutator between this is 2i times sigma z. Okay, so this is what it means by commutator. So that means these two are incompatible. Okay, so actually for this part here, if you are confused, if you're already like very stressed about the other earlier parts of Hilbert space, the bra-ket things, then this part, if you can ignore this for now, at least for now, because we will not use this yet until chapter 3 or 4. Yeah, we will not use this until chapter 3 or 4. So, but because I'm talking about the postulate, we are establishing the rules of the game. So I write down the rules here first. Then when we do chapter 3 or 4, then only you can look at this again, right? If you want, you can focus on the earlier things that we were discussing. So does anyone have any question so far? Okay. So now, because we are talking about postulates, so we are writing down the rules that we are about to follow later. So this is kind of like a lot of the things from the end of the course to the beginning of the course, all are listed down as postulates, which we will use at various points. So V has come to postulate 5, basically. Okay, so postulate 5 is basically just Schrodinger equation, or just to like make more fancy words come out. Like writing fancy words and in an official way is also a skill that you need to practice, you know, because when I'm teaching you guys, I use like the simple words like dagger and things, so that's easy to remember. But when we talk to other people, they may not understand. So the official language is something that everyone understands around the world. We are talking about the time evolution, right? The Schrodinger equation describes how they evolve over time. This is like Newton's second law. Given a force, what is the acceleration that will determine how they evolve over time? So same thing happens here. Time evolution of a quantum system obeys the Schrodinger equation. Okay, so this is going to be the most important equation of our course, because everything that we solve here, it must obey this equation, right? This is like the Newton's law of mechanics. Here is our Schrodinger equation. And what does it look like? So it looks like this. So IH bar. Okay, so already the complex number comes out, right? And H bar is what I talk about, H over 2 pi. And it is the time derivative of the ket, because now I'm talking about quantum system that might change over time, right? If it's an electric field, then it will do this. If there is a potential energy, then there's a force. So it will change over time. So the state of the particle will change over time. And on the right hand side is given by H psi. So H is an operator, which we call the Hamiltonian. Okay, so this is a Hamiltonian, and it is a so we will come to the details later, but for the moment, let us understand that this is an operator for the observable of energy of the system. So have you heard the word Hamiltonian before? Is there something you're familiar with? Sigma Z is general. It's a pure yes. So sigma Z, yeah, back to sigma Z for a while, right? So sigma Z is measuring the spin, right? So I got my 3 axis. Depends on what you mean by general, right? So if I want to the rotation of an object, right, has some angular momentum. So I got the Lxi, Lyj, Lzk. Okay, so I can measure the components of this vector by sigma z, sigma y, sigma x. So it's just the x, y, z components, right? So it's the direction, but in general, is any object will have the different x, y, z components. So this is my sigma over here. Okay, so these are just examples of operator, but why sigma x, sigma y? Actually, we will come back to this later, right? So this is why I said don't worry too much about this part yet. It's just like a preview. But what was the other question? You heard it before, but no idea what it meant, right? So yeah, so So now finally we get to explain. So this is named after the physicist called the, ouch, I dropped my pen. Here's this one, William Hamilton. Okay, so this one is actually, you will learn this towards the end of theoretical mechanics. So theoretical mechanics, you will learn something like the Lagrangian, Lagrangian, and then after Lagrangian you will learn about Hamiltonian, and then it will be the same Hamiltonian that is here. So all these are like very alien language. Again, don't worry about it. For us now, right now, we are learning the quantum mechanics. It just says that this is the energy of the system. Okay, so don't worry about it. It just means energy of the system. That's all, right? So nothing special about this. Okay, so it is an operator. So an operator also, it should have eigenstates, right? And the eigenvalue will tell me the energy of the system. I keep saying the hydrogen atom example. There is a Hamiltonian for the hydrogen atom. One of the state is the ground state. The eigenvalue is 13.6 eV, which you have already learned in modern physics, right? But in fact, I call this the Schrodinger equation. Maybe you might find it strange. You might, in other courses, the Schrodinger equation for the physics student, if you take PHY 104, the Schrodinger equation is actually different from this, right? The Schrodinger equation is actually looking like this. H bar squared over 2m, the mass of the object, the x squared, and then plus the potential plus the psi. So why is it so different from this? This is actually a special case. So for the math student also, don't need to worry, because we actually going to a more fundamental level. We start from this, right? And then we see why this comes out when the physics student were doing this last time. But we will focus on this for now. So this is the more important thing, right? So this is the more important form of our Schrodinger equation. And this is why we spend so much time learning about the Hilbert space and all this thing, because the Schrodinger equation is expressed in terms of the ket, how ket changes over time. Yeah, got back my pen. Okay, so that is our Schrodinger equation. Yeah, Hamiltonian. This Schrodinger equation looks more high class, right? Yeah, because the bra-ket notation looks very cool, right? Like my friend always says. More, yeah. And more elegant and simple, easy to remember. This one has a bunch of stuff. I need to think for a bit to remember. You know how I didn't memorize this, but I know how this works. So I think a bit, okay, H is, I can convert H into this. We will learn how to do this in chapter 3, right? And the left hand side is the same, but the left hand side, this is not in the Hilbert space, but here is in Hilbert space. So how to go from here to here is actually very interesting, and a lot actually comes from classical mechanics actually. So even though quantum mechanics is strange and things, but we are still using classical mechanics concept. Hamiltonian, things like that. This is actually classical mechanics. You haven't learned it yet, but it's classical mechanics actually. Okay. Yeah, so I think we run out of time already. So, but we have finished chapter 1. So the next thing we'll do is, a lot of the things are abstract stuff, you know, like bra-ket and things, a lot of math stuff. But in the next class, we go to chapter 2. We will apply all this concept to actually solve a real problem. So in chapter 2, we solve 2 problems. Firstly, we will solve the Stern-Gallac experiment, and then after that, we talk about the ammonia maser. So 2 cool experiments, pretty fun things to solve. Okay, so yeah, I think that's it. Thanks again, everyone, today for presenting. And don't worry, yeah, so don't worry if you got the wrong answer and everything. That's not our main point, right? So don't worry about marks for wrong answer. I don't care about that thing, right? The main point is the presentation. But otherwise, that's all for today. So see you guys on Thursday.